Welcome to demo video 2 in our course B09 and R for AI. Here we're going to talk about getting data and exploratory data analysis. So here what we're thinking about is using different R packages to manage, organize, import, and visualize our data. So tidyverse is very good for um, organizing our data, ggplot for visualization, dplyr for manipulation, and readr for importing it. We're going to use the Tidy Models umbrella of packages that are relevant for performing simple um, machine learning using R. So we have R sample that splits the package that splits data into the testing and training and validation data sets if we need that. We have recipes, which is useful for pre-processing the data, including scaling it, because the initial ranges will be different, and encoding it appropriately and imputing missing data if that's relevant for you. For Parsnip, we can use fit models with a unified interface, which means we can then perform prediction and measure model performance using the test data set we separated at the start. We can track our workflows using the workflow package, which creates a recipe for what we're trying to do. And we also tune our model using the tune package, which we're not going to cover in this course. So we can install the Tidy Models package, which is an umbrella for these different ones, and Tidyverse as well as the other packages too. We can load Tidy Models and then load Tidyverse too. And what we'll do is set a seed to make sure that we get the same results if we use this particular value. If we change that value to a different one, the seed will be different, which means that the initial values for when tools start may result, just like cooking, in a slightly different result at the end. So our goals here are to get the raw data, use base R packages to do exploratory data analysis, apply linear models using base R, split that data into testing and training using R sample, pre-process training data using recipes, fit the data using Parsnip and make predictions using Yardstick on the test data at the end, and then put this all together at the end. So the data we're using is based on hypothetical bacteria, where we have the colony size, growth rate, and zone of distribution for our samples that are R and S, i.e. they're classified as resistant to a particular substance or susceptible. So we're trying to apply our model to this data so that we can predict for the test data set, are they R or S in terms of their classification? That's the key question. So our approach is quite applicable to different things. So if we had, for example, a question over whether the mean of the minimum inhibitory concentration of group A versus group B is different, um, we might use a statistical approach using a t-test or ANOVA or something like that. That's like my isolates grouping into different innate groups. We might use something like some sort of unsupervised clustering method or visualization method. It could use machine learning, but that's not necessary. If we had a more AI-centered question where we're trying to ask which 50 genomic features best explain the MIC, we might use a form of regression, such as lasso regression. And then if we're asking, for example, can I predict resistance properly from 20 features? We can use machine learning supervised classification for this to see if that actually works effectively. So what we're going to do here is create a table of data using Tibble, where we're creating identifiers for each isolates, each of the 2,000 isolates, 1,000 of which are S and 1,000 of which are R. We're going to use rnom to generate this data. The first 1,000 are S, the second 1,000 are R. The R have a bigger um, diameter of colony size. And then same for the growth rates, the R are a bit bigger than S, but they overlap to an extent. And the zone of inhibition, again, S are bigger and R are a bit smaller. And we add labels onto this data so we can distinguish between the two data sets more easily. We can use this data then to perform numerical summaries by outcome group using dplyr, where we pipe the pathogen S table to group by the outcome. So that's the outcome is either S susceptible, R for resistant, and summarize it. That means we'll have the mean diameter is one metric that we can extract from this data. Another is the mean growth rate. Another is the mean zone. And you see down below that we've laid out these results where the R has a higher mean colony diameter, a higher mean growth rate, but a lower mean zone of inhibition. We can also plot this data, and we'll talk about it with our R code shortly, and perform numerical summary. So let's switch to the RMD, our student environment, to look at our RMD file. Over here we have our RMD file, which is on the course folder for you. We're going to use our tidy models and tidyverse. We can run the library command to install them here on lines 36 and 37. You should not see any output when they've been correctly installed, and we'll set the seed for B to be 42. Those are packages, and we can go down to the part where we're thinking about the first steps, which is to make the data. So here we're using rnorm, which generates a vector of data. So if we use the rnorm function, it will generate like this, 1,000 values with a mean of 3 and a standard deviation of 0.5. So you can see these values are round 3, they're not exactly 3. And if we did a histogram of a random set of these values, they are centered around 3. If we can toggle the breaks to show this more clearly, so you can see that on average, they're going to have that shape, but it's not always the exact same every time we do this. There's some variation. So we do this for the two groups where they're intrinsically different, and we can run this line and then check our data at the end. We can also view our data to see what it looks like inside. We see there's a range of values for the diameter, where they are of a higher value than S on average. The growth rate is lower for R and higher for S, and the zone is higher for S and lower for R. So that's our data. Then we can summarize it by outcome for these values. So we're getting the data from the mean diameter to get the mean diam value, and then we can plot that. So you see here we have the values between the two different groups, and then we can visualize it. What we're doing here with pivot longer is to convert it to a long format. So if we take this bit of code, we're converting it to a format such that we have one value per row. That means for each particular sample, we have 3 entries for each of the 3 metrics that we have. So for S1 here, what we see is that we have diam, millimeters, growth rate, and zone, each on different rows. So each row is one value only, and those are listed here. We can see for diam and growth rate and zone, they're quite different from each other, so therefore we can't plot them on the same plots. Effectively, it's not really going to look very good. So what we're going to do is create our plot initially with the ggplot function, and that basically creates the blank canvas onto which we can put our plots. You see this is our blank canvas. We can add on a box plot to differentiate the two different groups. However, what we'll see inside the box plot is that the ranges look quite peculiar, especially when we add on geom jitter. And you can see the jitter points are shown, and there's distinct categories within there. So what we need is facet wrap that will take each feature and scale them freely in terms of the y-axis. So we've got 3 separate plots here, 3 panels for between resistant and sensitive. And then what we can do with these is plot them as colored as orange and blue. So now we see a new color scheme, and we can add a title and also white theme minimal to arguably make it easier to read. So you see white background, and you see the title, and then have no legend, just to again to maximize the space for the groups, because the legend is easy there. So that's one way of visualizing it, just to see what the data looks like. And that kind of completes this part on EDA. You can look further at the course material for ST9 exploratory data analysis. And our next video will cover on linear regression.